right, so this is some material that I think can be very relevant in life and to whatever career you choose. It certainly helps you make good and wise choices. The expected value is often referred to as the long term average or the mean. In other words, how things will probably work out over time. This is used constantly in sports, it is used anytime you're managing large numbers of things. This means that over the long term, doing an experiment over and over and over, in other words, large numbers of things, you would expect this average to more or likely work its way in. So, the expected value is often referred to as the long-term average or mean. This means that over the long term of doing an experiment over and over, you would expect this particular average. You toss a coin and record the result. What is the probability that the result is head? It's a half, 1 out of 2. But the truth is, just because you flip a coin twice doesn't mean one of them is going to come up heads. All right, if you flip a coin 2 times, does the probability tell you that these flips will result in exactly 1 head and 1 tail? You might toss a fair coin 10 times and record 9 heads. As you learned in table 288, probability does not describe short-term results. It is long-term. So a good example of that is this guy named Carl Pearson, who apparently had a whole lot of time on his hands. And he tossed a fair coin 24,000 times. He recorded the results of every single toss. And the time it took to count this up, 12,012 times it came up heads, which is just about exactly what you'd expect. You'd kind of expect 12,000 times it would come up heads because half of 24,000 flips is 12,000 and the probability is a half. Okay? The law of large numbers states that as the number of trials in a probability experiment increases, the difference between the theoretical probability, which like for flipping a coin it's 1/2, and the relative frequency approaches 0. In other words, they become pretty much the same exact thing. Another example would be if you roll a die 6,000 times, the probability of getting a 3 is 1/6, so you'll probably get about 1,000 threes. They get closer and closer and closer to the same. 1,000 out of 6,000 is pretty much the same as 1 out of 6. It is the same. And you're probably going to get pretty much 1,000 rolls. Okay? All right. So 2 other things you should know is this long-term average is known as the mean or expected value. The mean and expected value is the same thing. And we use this Greek letter mu. See that symbol there after the words Greek letter? In other words, after conducting many trials of an experiment, you would expect this average value. Okay, so a men's soccer team plays, of course they play soccer, 0, 1, or 2 days a week. The probability that they play 0 days is 0.2. The probability that they play 1 day is 0.5. And the probability that they play 2 days is 0.3. Find the long-term average you can expect. Now, this is one of those situations where there is a formula to follow, but I think if you just think the context through, you could figure this out without ever attempting to follow any particular formula. And let me show you what I mean by that. So, first let's go through my explanation, then let's go through the formula, and then let's reconcile the two. So, look, the possible things are 0, 1, and 2. Those are the possible outcomes. The probability of a 0 is 0.2. The probability of a 1 is 0.5, and the probability of a 2 is 0.3. So look, if the probability of getting a 0, and of course that means they don't play at all during that week, if I multiply them, I get a total of 0. If I then say, well, the probability of playing once a week is 0.5, and I'm only going to play that 1 time, then that would be 0.5. And the probability of playing twice a week, that would have to be 0.3, but you'd have to do it twice. So you multiply that by 2 and you get 0.6. So you add that up and you say, okay, well, if I add them all up, I get 1.1, which suggests, on average, when you consider the probability of playing 0 times, the probability of playing 1 time, and the probability of playing twice, when you add up all those probabilities and all those things that would have to happen, and you work it out over time, you would expect to play about 1.1 times per week. So in other words, If you played for 10 weeks, you'd probably play 11 games, a little more than once a week. And doesn't that make sense that you would play a little more than once a week? Because if we look at these figures, the highest figure is playing once a week, probability 0.5. And the probability of 0 is a little bit lower than the probability of a 2. And that little bit more of a probability of playing twice a week is what bumps this from playing 1 game a week, which is the most likely outcome, to 1.1 is the expected actual value that you would get out of there. Okay, so let's go back and let's look at this using the formula. So the formula says, first you want to construct a probability distribution frequency table. And what you're going to do is the outcomes are 0, 1, and 2. The probabilities are 0.2, 0.5, and 0.3. And then you add a column, which is x times the probability of x. And that's this last column here. Following the formula, x times x, the probability of x means just multiplying it. I get 0, 0.5, and 0.6. And then to find the long-term average, all you do is add up this last column, and that tells you how many times you can expect to play per week, which is 1.1. The expected value is 1.1. The men's soccer team would, on the average, expect to play 1.1 days per week. The number 1.1 is a long-term average. It doesn't mean that's what you're going to play every single week. We say if you put it for the season, like a school year is 40 weeks long. If a soccer season was 40 weeks long, you'd expect it to play 1.1 times per week, or 44 games in 40 weeks. Okay? All right. So let's take a look at one more example before we stop this video. Here is a probability distribution table for a newborn sleeping after midnight. I would like to see you figure out the values for x times the probability of x. Remember, x is 0, the probability of x is 2/50ths, and so on. So let's do stop and start, but just on that column. Go ahead. Okay, so multiplying those numbers out, I'm going to get 0 times 2/50ths, okay? 1 times 11/50ths, 2 times 23/50ths. Again, I'm multiplying the column on the left with the next column in, the first and second columns. The third column and so on. Now, if I add up all of these numbers, okay, I come out with 1157, 6484, 105. I come up with 105 in 50 weeks. And if I just do that division, 105 divided by 50, I get 2.1. Okay, and that's why they expect it to occur 2.1 times per week. All right, so now there's a next column to figure out. And this column is kind of like we're getting into standard deviation work. Okay, if you remember when we did standard deviation work, we said that you subtract the mean from the actual value and you square it. And then eventually we would come back and square root it all. Well, we're going to do that this time, but we're also going to add in the probability of x. So you just follow what it says to do right here. Okay, what it says to do right here is the value, which in this case is the x column over here, minus the mean, and then square it. So for the first column, you would get 0 minus 2.1, and then you would square in parentheses and square it. Make sure, super sure, that this is in parentheses. Otherwise, a negative could come out completely wrong on you. Okay, so figure that out for the whole all the numbers from 0 to 5. We helped you out with the first one. It's 0 minus 2.1 squared times 2/50ths. I'll help you out with the second one too. It would be 1 minus 2.1 in parentheses squared times 11/50ths, because that's what the probability is. Okay? Finish out the rest of the column. Doing stop and start, of course. Okay, so here's what the column comes out to. In each case, all you're doing, look what this formula says. This formula says take the x value, subtract the mean, and square it. Take the x value, subtract the mean, which is 2.1. Notice every time it's 2.1. because the mean was 2.1. And each time these scores change from 0 to 5 because that's where the x goes. And x is listed over here as the particular number of times the newborn wakes at night. So that's 0 through 5. So in each case, I just subtract the mean and square it. Now, that's extremely important because it fits in with our concept of standard deviation. Remember, what squaring does, and then later we will square root it, is it just makes everything positive. And all we're trying to do is find the distance away from the mean, okay? All right. So you add the values in the third column of the table to find the expected values of x. That's the 2.1 that we figured out before, okay? And now we're finding the standard deviation right here. Using, to complete the table, we now figure out what the standard deviation works out to be. If you add up all of those numbers, you're going to get 1.05. And then I have to square root it. So remember what we said with standard deviation. You add them up and square it, then you square root it. And this works you through the whole problem. Just like you added up the values in the third column and then divided by 50. In the fourth column, you add up the values and then you square root. Okay? That gives me 1.0247. Okay? So the expected mean probability formula is right here. And the standard deviation formula is right here. Okay? So when you need formulas, you will be given formulas. And we're going to come back to the standard deviation thing in a little bit and revisit it in a way that I think is even a little easier to understand. Okay, I'm going to stop it at this point and we'll start the next video at this point. But I'm running out of memory in order to fit the video up on the website, on Moodle.